Hello friends, today we are going to discuss about one important topic of complex analysis known as analytic functions. So in this video we will show how to show that given function is analytic at a given point. So before discussing those type of examples, first we define what is definition of analytic function. So suppose we are given some function of complex variable, or suppose we are given some complex function f of z, and let z0 be any complex number in the complex plane. Then this function f of z is said to be analytic at this point z0 if we can find out at least one circle whose center is z0 such that the function is differentiable at every point in that circle. I repeat again, the function is differentiable at point z0 if we can find out at least one circle with center z0 such that the function is differentiable at every point in that circle. The function is differentiable at every point inside that circle. Don't worry about the boundary of the circle. And the set of all points inside the circle is known as neighborhood of z0. The set of all points which are inside the circle with center z0 is known as neighborhood of z0. So in other words, the function f of z is analytic at point z0 if there exists at least one neighborhood of z0 such that the function is differentiable at every point in that neighborhood. So this is the definition of analytic function. A function f of a complex variable z is said to be analytic at a point z0 if the function has a derivative at each point in some neighborhood of z0, or we can say that the function is analytic at a point z0 if we can find out at least one neighborhood of z0 such that the function is differentiable at every point in that neighborhood. And if we talk about analytic function in a domain, so if D is any domain in the complex plane, then the function is analytic in that domain D if f is defined and differentiable at all points in that domain D. So we see some examples of analytic function. If we consider polynomial function f of z equal to a0 plus a1z plus a2z square plus an z raised to n, where a0, a1, a2, an are complex constants and z is a complex variable. So we know that the polynomial function is differentiable at every point in the complex plane. So if we consider any point in the complex plane, and if we want to check whether this is analytic at that point, then we can always find out at least one neighborhood of that point such that this function is differentiable at every point in that neighborhood, because the function is differentiable at every point, so it is differentiable in any neighborhood of any point. So if we consider any point in the complex plane and the circle with center as that point, then this polynomial function is differentiable at every point in that neighborhood, because the function is differentiable at every point in the complex plane. So therefore the polynomial function is analytic at every point in the complex plane because it is differentiable at every point in the complex plane. So we consider another example. We have discussed this mod z square function. In earlier lectures we have shown that the function mod z square is differentiable at only one point, origin. So we know that mod z square is differentiable at z equal to 0 only. So it is not differentiable at every non-zero point. If z is non-zero, then mod z square is not differentiable. So if function is not differentiable at a given point, it can never be analytic at that point. The points at which function is not differentiable, function can never be analytic at those points. So function is not analytic at every non-zero point. Now function is differentiable at z equal to 0, but to be analytic at z equal to 0, we have to find out the existence of at least one neighborhood of 0 such that the function is differentiable at every point in that neighborhood. So here we are not able to find out any circle with center 0 such that the function is differentiable at every point in that neighborhood. The reason is this function is differentiable at only one point, z equal to 0. Because the function is differentiable at z equal to 0 only, if we consider any circle however small with center as z equal to 0, then in that circle there are other points except 0, and function is differentiable at z equal to 0 only. Therefore function can never be analytic at z equal to 0 also. Keep in mind, mod z square is differentiable at z equal to 0, but it is not analytic at z equal to 0 because we are not able to find out any neighborhood of z equal to 0 such that function is differentiable at every point in that neighborhood. So mod z square function is not analytic at any point, and the function which is not analytic at any point can be known as nowhere analytic function. So nowhere analytic means it is not analytic at any point in the complex plane. Another example is the function conjugate of z, that is z bar. So if we can recall that z bar is nowhere differentiable. This we might have discussed in earlier lectures, or you can decide using Cauchy-Riemann equations that z bar is nowhere differentiable. The function z bar is not differentiable at any point, and so we can write that z bar is nowhere differentiable in the complex plane. So we can say that z bar is nowhere analytic because it is nowhere differentiable. Analytic function is also known as regular function or holomorphic function. So remember these names also. Sometimes in examination they can ask in this way also, regular function or holomorphic function. They can ask that check whether given function is holomorphic or regular. Instead of analytic, sometimes they are using these words also, regular or holomorphic function. Next definition is entire function. So the function which is analytic at every point is known as entire function. So a function f is called entire if it is analytic at each point in the complex plane. So famous example is polynomial functions are entire functions because they are analytic at every point. So let us take this example number 1. Show that f of z equal to x into y plus I into y is nowhere analytic. So to show that function is nowhere analytic, first we have to determine the number of points in the complex plane at which given function is differentiable. So for determining those points, the points at which function is differentiable. So we have to first determine the points at which Cauchy-Riemann equations are satisfied. Using those points we will able to decide the points at which function is differentiable, and using differentiability we will be able to decide analyticity of given function. Here it is given that function is nowhere analytic. You have to prove this. So first we find out the points at which function is differentiable using Cauchy-Riemann equations. So if I compare this with u plus iv, then I obtain u equal to x into y and v is y. And using this partial derivatives, del u by del x is y, derivative is with respect to x, so y is constant, derivative of x is 1 with respect to x. Similarly, del u by del y is also x, because if we differentiate with respect to y, we consider x as constant, so x is constant, derivative of y is 1. Similarly, del v by del x is 0 because there is no x term here, and del v by del y is 1. Now we decide at which points ux and vy are equal. So ux equal to vy if y equal to 1. That means this equation is satisfied at all those points whose y component is 1. So there are infinite number of points having y component equal to 1, and those points lie on the line y equal to 1. Suppose this is x axis, so that we can represent by y equal to 0. If this distance is 1, then this is the line y equal to 1, and on this line every complex number has y component 1. For example, if this distance is 1, this point is order pair 0 1, so this point is on the line y equal to 1. So this equation is satisfied at all the points on the line y equal to 1. This is y axis, or we can write it as x equal to 0. Similarly, we determine the points at which second equation is satisfied. So second equation is uy equal to minus vx. So if you compare uy with minus vx, you will obtain x equal to 0. So uy equal to minus vx if uy is x and minus vx is 0. So if x equal to 0, that means this equation is satisfied at all those points whose x component is 0. And these points are on the y-axis. So this equation uy equal to minus vx is satisfied at all the points on y-axis, and ux equal to vy is satisfied at all the points on the line y equal to 1. So we have to determine the common point at which both equations are satisfied. So one equation is satisfied on this line, another equation is satisfied on this line, and the intersecting point of both the lines is order pair 0 1. So this is the only point which is on both the lines. That shows that Cauchy-Riemann equations are satisfied at order pair 0 1 only. That means Cauchy-Riemann equations are not satisfied at every point z which is not equal to 0 1, or we can write 0 1 as, in complex notation, it is I. So if z is not equal to I at every point which is different from I, CR equations are not satisfied. That means function is not differentiable at every point except z equal to I. And we can see these partial derivatives are polynomial functions, and they are continuous at every point, therefore they are continuous at 0 1 point also. So that shows that function is differentiable at 0 1 only. Okay, here this is a mistake. Both Cauchy-Riemann equations are satisfied at 1.01 only, and partial derivatives are continuous at 0, 1. Therefore, function is differentiable at point 0, 1 only. This is the only point at which function is differentiable. Now to check analyticity at this point, the points which are different from this, at those points function is not differentiable, so function can never be analytic at those points. Now function is differentiable at this point 0, 1. So for this point the function is analytic if we can find out at least one circle with center as this point I, such that function is differentiable at every point. But it is impossible. If I consider any circle with center as this point, order pair 0, 1, then there are infinite number of points in that circle which are different from center I, and function is differentiable at only one point I. So if we consider any circle with center I, then there are infinite number of points in that circle at which function is not differentiable. So we cannot find out any circle with center as I or order pair 0, 1 such that the function is differentiable at every point inside that circle or at every point in that neighborhood. Therefore, function is not analytic at order pair 0, 1 also, and function is not analytic at every point which is different from order pair 0, 1. So therefore we can say that f of z is not analytic at any point, or f of z is nowhere analytic. So in this way we can decide the analyticity of a complex function. I hope you like this lecture. In the next lecture we will do some more examples on analytic functions. Thank you very much.